Hello everyone, welcome to our presentation on the removal of Tartrazine solution by used coffee grounds as a source of activated carbon. My name is Nadzifa, Alifia, and I'm here with two of my partners, Rifqi and Levana. First and foremost, I want to thank TICA for the opportunity to present our research and also Institut Teknologi Bandung's Bioengineering Department for helping us to get to this point. Here is the outline for our presentation, and with that said, let's dive right in. And to Levana, go ahead.
When I was young, my mother walked me from school after class. We walked on an alley which has gutter on the left and right side. We can know which house that manufactured clothes from the colored waste on the gutter. This is not happening in just one or two houses, but also in a large-scale industry. Unfortunately, many of them don't pay a good attention for this problem because of the high waste treatment prices that can decrease their net income. Synthetic dyes are produced nearly 800,000 tons per year worldwide, but about 10 to 15% of dyes are disposed while being processed in the industry. This waste causes harm to the environment and humans if not treated properly due to its toxic nature.
That is why our team tried to improve one of the most potential methods to treat dyed waste by absorption using spent coffee grounds as adsorbents. Why coffee grounds? Coffee ground is one of the most abundant waste produced to date, with 9.5 million global shipments of coffee beans in 2018, where 50% of them are in the form of coffee grounds. Spent coffee grounds are activated to increase its absorbing abilities. In this study, we seek to determine the feasibility of using used coffee grounds as an activated carbon source to absorb tartrazine. And from there, we broke it down to two specific goals. First, which is determining the RL and KL values of the Langmuir adsorption isotherm. And second is determining the most effective time of 3, 5, or 7 hours of activation through determining the ineffective bedtime. To conduct this experiment, there are three main steps that were executed. First, we collected the coffee grounds, and then we prepared active coffee grounds by drying it first in an oven at a temperature of 100 degrees for an hour, just to decrease its initial moisture content. The dried coffee grounds are then put into aluminum containers, sealed, and then put in a furnace at 300 degrees for 3 hours to undergo the pyrolysis process. The results are charred coffee grounds. The charred coffee grounds were sifted into a 60 mesh size to reach uniform particles, and then the zinc chloride solution was prepared for activation. At a concentration of 25% weight per volume, the solution was separated into 3 different beakers, each beaker for each activation time, 3, 5, and 7 hours. After that, the activated charred coffee grounds were dried at room temperature. Then, it's the determination of the ineffective bedtime on tartrazine absorption. Initially, a standard concentration curve is made with the help of spectrophotometer at a wavelength of 480 nanometers. The experiment was run using this setup. 1.5 grams of activated charred coffee grounds was used for each run, each trial. The synthetic dye solution was fed into the column continuously, and the nozzle at the bottom was opened to allow the dye to discharge from the column into test tubes, and then the test tubes were switched every certain amount of time to collect each sample. The absorbance of the dye was then calculated with the spectrophotometer to determine its concentration using the standard curve that was made earlier. The concentration is used to determine the breakthrough curve of each adsorbent variant.
Next, we determined the adsorption isotherm using an array of tartrazine solution that was prepared with concentration of 500, 1000, 1500, 2000, and 2500 ppm. 15 milliliters of each solution was mixed with 1.5 grams of the activated charred coffee grounds in an aromayer flask. The mixtures were placed in an incubator shaker at a controlled temperature of 37 degrees Celsius and a rotation of 100 rpm. After 11 hours, each solution's concentration was calculated to get the data needed to determine the adsorption isotherm of the adsorbent. From the experiment, we find that the favorability of this adsorption can be defined by Langmuir isotherm. Adsorption isotherm gives an idea to how the adsorbed solutes are distributed in the liquid phase and the solid phase as the adsorption reaches equilibrium. Langmuir isotherm explains adsorption in a manner that it only happens with the formation of monolayer of adsorbate on the outer surface of adsorbent. After one layer is formed, no further adsorption takes place. Langmuir isotherm also assumes uniform surface and consequently uniform energy used for adsorption. The linearized form of Langmuir isotherm is expressed in this equation.
Determination of those parameters are by plotting the value of 1 per QE to 1 per CE and taking the interception to determine the QO or the maximum mononuclear capacity and KL, which is the Langmuir constant. In addition to that, we also determine the dimensionless parameter of RL to explain how the equilibrium characteristic is. RL is defined by the equation shown on the slide, and CO is the highest initial concentration used in this experiment. Fitting of experiment data to Langmuir isotherm graph is shown by the graph in the slide. Parameters estimated from this are QO, the maximum molecular capacity, which is 27.4 mg solutes per gram of activated carbon, and then KL, the Langmuir constant is 0.007, the RL is 0.04, and this fitting has the R-square value of 0.94. The results shown that the RL value of the adsorbent is between 0 and 1, which means that it is favorable process. An RL is approaching 0 represent an irreversible adsorption process, where the adsorbent has a high affinity towards the contaminant. The value determined from this experiment shows a relatively low value, which means it has a great adsorption characteristic. We also determine the effect of activation time on ineffective bedtime by plotting the final concentration to the initial concentration against time, shown in this graph. Based on the data presented, charred coffee grounds activated with activation time of 5 hours has the most effective compared to 3 hours and 7 hours. This is shown by the longer ineffective bedtime, shown by the later inflection point is in the graph. Activation time of 3 hours indicates the lack of activation time, which means there is not enough pores or there is not enough surface area to accommodate the adsorption process, whereas the 7 hours has an excessive activation time, which means that the pores has already collapsed, so there's not enough surface area either. The adsorption capacity for 5 hours is 27.4 mg tartrazine per gram of activated carbon. So in conclusion, the experiment shows that coffee ground waste is potential to be used as activated carbon source to remove tartrazine from a solution. It is also found that 5 hours is the most optimal time to do the activation process compared to 3 hours and 7 hours. Using a fixed bed system, 5 hours of activated carbon source has the ineffective bedtime of 6 minutes and the maximum molecular capacity of 27.4 mg solutes per gram of activated carbons. This activated carbon are also shown to comply with the Langmuir isotherm adsorption model with the R-square of 0.945, indicating a favorable process of adsorption. All in all, ground coffee waste has the potential to be implemented in a larger scale of the tartrazine waste treatment.
Thank you very much for your attention. We hope to see you in the future. If you have any future questions or further questions, please feel free to contact us.